Thank you for listening. This course was created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional podcasts, books, newsletters, and cool merchandise await. Let's get started. Monitoring serves as the continuous oversight mechanism for deployed artificial intelligence systems, ensuring that they perform reliably after leaving the laboratory. Its primary purpose is to detect failures before they escalate, providing a real-time safety net that protects users and organizations alike. Effective monitoring offers assurance to stakeholders and regulators that systems remain aligned with their intended goals, even as data and contexts evolve. It is not sufficient to test models once before deployment. Environments change, inputs shift, and threats evolve. Monitoring ensures that risks are caught early and addressed proactively, rather than discovered only after harm has occurred. In this sense, monitoring is the operational extension of governance, translating principles of responsibility into daily practice. To understand why monitoring is necessary, one must grasp the concept of drift. Drift refers to changes in data or patterns that cause a model's performance to degrade over time. Data drift occurs when the incoming inputs differ from the distributions the model was trained on, while concept drift describes changes in the underlying relationships between variables. Label drift happens when ground truths evolve, such as when categories of behavior or diagnosis standards shift. Drift may be subtle, accumulating gradually, or abrupt, appearing suddenly after a major environmental change. Regardless of pace, drift threatens the reliability of AI systems, making ongoing detection and adaptation essential. Monitoring provides the lens through which drift can be identified and addressed before it undermines outcomes. There are multiple types of drift that monitoring must be designed to capture. Data drift arises when the characteristics of incoming inputs change, such as different demographics entering a system over time. Label drift occurs when the definitions of correct outputs shift, reflecting evolving standards or practices. Concept drift represents deeper changes in how inputs relate to outputs, such as shifts in market behavior or disease patterns. Feedback drift occurs when the model itself influences the data it receives, reinforcing biases or narrowing its exposure to diversity. Each type of drift requires different detection and mitigation methods, underscoring the importance of designing monitoring systems that are comprehensive rather than narrowly focused. Without attention to all these forms, hidden weaknesses may persist unnoticed. Metrics form the backbone of monitoring, offering quantifiable indicators of system performance and reliability. Accuracy and error rates are fundamental, but continuous tracking provides more meaningful insights than static benchmarks. Calibration checks are particularly important for models that produce probability outputs, ensuring that confidence levels reflect actual likelihoods. Fairness metrics must be included, evaluating whether performance is consistent across demographic subgroups. Reliability indicators, such as stability under changing conditions, provide another layer of assurance. Tracking metrics over time allows organizations to identify trends, spot early warnings, and understand whether interventions are working. Metrics turn monitoring from an abstract concept into actionable evidence, guiding decisions about retraining, recalibration, or rollback. Monitoring infrastructure provides the tools and systems that make oversight possible at scale. Dashboards allow stakeholders to see real-time health indicators, translating complex performance data into accessible formats. Automated alerts highlight anomalies or threshold breaches, ensuring that issues are escalated promptly. Logging pipelines capture the details of model decisions, creating audit trails that support both technical troubleshooting and governance compliance. Cloud-based monitoring solutions provide scalability, enabling organizations to oversee multiple models across diverse deployments. Together, these elements form the nervous system of AI oversight, ensuring that models remain observable, accountable, and under control even in dynamic environments. Without infrastructure, monitoring remains aspirational. With it, monitoring becomes a disciplined operational practice. Monitoring is not limited to outputs. It also extends to data quality, which underpins the trustworthiness of AI systems. Systems must track completeness and consistency, flagging missing or corrupted data before it compromises results. Unexpected distributions in inputs, such as sudden surges in outlier values, may signal errors in pipelines or shifts in the environment. Failures in data pipelines, whether due to technical breakdowns or human error, can introduce silent vulnerabilities that only monitoring will detect. Governance frameworks increasingly require organizations to document how they track and safeguard data quality, recognizing its foundational role in responsible AI. By embedding data quality checks into monitoring, organizations ensure that models are not only functional but also grounded in reliable inputs that reflect intended use. Model performance monitoring focuses on ensuring that predictions continue to align with real-world outcomes over time. One common approach is to compare model outputs against actual results, such as checking whether predicted credit defaults match observed repayment behaviors. Subgroup analysis is also important, revealing whether disparities in accuracy or error rates emerge for specific demographics. Operational factors like latency and throughput are part of performance monitoring as well, since models must deliver timely results to remain useful. Rolling windows of analysis allow organizations to track trends and identify gradual shifts in performance that may not be visible in single snapshots. This continuous view transforms monitoring from reactive problem-solving into proactive quality assurance, ensuring that performance degradation is caught before it becomes systemic. Monitoring bias is a critical component of responsible oversight, as even well-performing models can perpetuate inequities. Continuous evaluation of fairness metrics ensures that disparities are not only detected during initial testing, but tracked over time. Alerts can be triggered when disparities exceed defined thresholds, prompting reviews and corrective action. Regular audits provide evidence of compliance with ethical standards and legal obligations, demonstrating accountability to regulators and stakeholders. At the same time, sensitivity must be balanced with practicality. Overly aggressive alerts may lead to noise and fatigue, while insufficient sensitivity risks missing real harms. Designing bias monitoring systems that are both rigorous and actionable ensures that equity remains a living part of system governance, not a one-time certification. Feedback loops complicate monitoring by creating situations where models influence the very data they are trained on or evaluated against. For example, a recommendation system that consistently suggests certain products may alter consumer behavior, narrowing the diversity of future data. Similarly, predictive policing systems can reinforce patterns of enforcement, creating self-fulfilling prophecies. These feedback effects can entrench biases and distort evaluations, making independent validation essential. Monitoring must account for these loops by periodically reintroducing external data sources or conducting counterfactual analyses. Corrective interventions may involve retraining with diversified datasets or redesigning feedback mechanisms to reduce reinforcement. By addressing feedback loops, organizations ensure that models evolve in ways that expand rather than constrain fairness and reliability. Incident detection represents the front line of monitoring, capturing moments when systems cross defined thresholds or exhibit abnormal activity. Breaches of accuracy, fairness, or reliability metrics should trigger reviews that escalate according to established protocols. Abnormal patterns in inputs or outputs may also signal adversarial activity or environmental shifts. Effective monitoring systems not only detect incidents but document them thoroughly, creating a record of when, how, and why issues occurred. Escalation paths ensure that incidents receive appropriate attention, whether from technical teams, governance staff, or leadership. Incident detection transforms monitoring into a real-time safeguard, ensuring that problems do not remain hidden or unresolved. It is the mechanism that links metrics to accountability. Remediation actions are the natural counterpart to detection, providing structured responses when monitoring identifies failures. Retraining models with updated or corrected data is a common response, restoring alignment with current conditions. Recalibration of thresholds may also be necessary to reflect new standards of reliability or fairness. In urgent cases, organizations may need to roll back to earlier model versions to prevent harm while issues are addressed. Communication to stakeholders is another vital step, ensuring transparency and maintaining trust even during disruptions. Remediation is not simply about fixing errors, but about demonstrating accountability through visible and documented action. Without it, monitoring risks becoming a hollow exercise that identifies problems without addressing them. Organizational responsibilities in monitoring extend across roles and departments. Data scientists and engineers must configure metrics, pipelines, and alerts to track relevant indicators. Oversight teams ensure adequate staffing and resources for continuous monitoring, preventing gaps in coverage. Leadership assigns accountability by embedding monitoring into governance structures, ensuring that it is not left to technical teams alone. Providing resources for infrastructure, whether open-source tools or enterprise platforms, is essential to sustaining monitoring at scale. By treating monitoring as an organizational function rather than a technical add-on, companies align it with governance expectations and stakeholder trust. These responsibilities emphasize that monitoring is not optional, but central to the safe and accountable use of AI systems. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Scalability challenges emerge as organizations attempt to monitor AI systems at enterprise scale. A single model may be manageable, but dozens or hundreds of models across multiple applications create complexity that strains both human and technical resources. Balancing cost with coverage becomes critical. Not every model requires the same level of monitoring, and resources must be prioritized for high-risk systems. Alert fatigue is another concern. If monitoring systems generate too many signals, staff may become desensitized and miss critical warnings. Prioritization frameworks help filter alerts so that the most important issues receive attention first. Ultimately, scalability requires thoughtful design that balances breadth with depth, ensuring that monitoring remains effective without overwhelming staff or budgets. Tools and platforms for monitoring are evolving rapidly to address these scalability concerns. Open-source libraries provide flexible solutions for configuring monitoring pipelines, often supported by active communities that update tools in response to emerging risks. Vendor platforms offer enterprise-grade features such as AI observability dashboards, anomaly detection, and automated drift detection. Integration with cloud-native pipelines allows monitoring to scale alongside deployment environments, ensuring that oversight grows with system complexity. Centralized dashboards connect monitoring data with governance teams, providing transparency and accountability across the organization. These tools represent the technical backbone of monitoring, turning theoretical requirements into operational capabilities that can support both compliance and trust. Documentation practices transform monitoring from internal activity into accountable evidence. Recording which metrics are used, how thresholds are set, and what incidents have occurred provides a traceable record that regulators and stakeholders can review. Capturing responses to incidents demonstrates not only that problems were identified, but also that they were addressed effectively. Logs and reports maintain transparency, ensuring that organizations cannot ignore or conceal failures. Sharing selected reports with stakeholders enhances trust, showing that monitoring results are taken seriously and used to guide improvement. Documentation thus plays both a technical and ethical role, signaling that monitoring is conducted with integrity and openness. Ethical implications of monitoring emphasize the responsibility to detect harm before it affects users or communities. Transparency in monitoring results ensures that hidden failures do not undermine trust or cause unacknowledged damage. Failure to monitor or to act on monitoring data risks, exposing vulnerable populations to disproportionate harm, violating ethical commitments to fairness and responsibility. Ethical monitoring supports informed decision-making, ensuring that users, regulators, and organizations can act on accurate information about system behavior. By embedding ethics into monitoring, organizations affirm that oversight is not only about compliance, but also about care for those affected by AI systems. This human-centered perspective elevates monitoring from technical maintenance to moral responsibility. Cross-functional collaboration is vital for effective monitoring, as responsibilities span technical, governance, and operational domains. Data scientists configure metrics and tracking systems, ensuring that monitoring captures the right indicators. Engineers maintain the infrastructure, keeping dashboards, pipelines, and alerts running reliably. Risk managers review monitoring outcomes, interpreting results in light of organizational exposure and compliance needs. Leadership ensures accountability by prioritizing monitoring at strategic levels and dedicating resources to sustain it. Collaboration prevents silos, ensuring that monitoring data informs not only technical teams but also governance boards and external stakeholders. By integrating multiple disciplines, organizations create monitoring systems that are both technically sound and socially responsible. Continuous improvement ensures that monitoring systems evolve as risks and technologies change. Techniques must be updated regularly to address new forms of drift, adversarial behavior, or regulatory requirements. Benchmarking against industry peers provides insight into best practices and highlights areas where monitoring can be strengthened. Learning from incidents, both internal and external, builds resilience by turning failures into lessons. Institutionalizing these lessons across teams prevents knowledge from being lost and ensures that improvements scale throughout the organization. Continuous improvement transforms monitoring from a static safeguard into a living practice, always adapting to keep pace with change. Without it, monitoring risks becoming outdated and ineffective. Regulatory alignment is increasingly shaping how monitoring and drift management are implemented. Emerging frameworks require organizations to demonstrate continuous oversight of deployed AI systems, especially those classified as high risk. Evidence of fairness monitoring is becoming an expectation, with regulators asking not just whether bias is checked, but whether it is tracked consistently over time. Some sectors already mandate reporting of incidents, such as financial services or healthcare, where harm from drift or failure can have immediate consequences. Anticipated AI-specific legislation is expected to formalize requirements for drift detection, bias auditing, and transparency in monitoring practices. Aligning monitoring with these regulatory expectations not only ensures compliance, but also strengthens trust with users and stakeholders by demonstrating accountability. Future directions in monitoring suggest increasing automation and sophistication. Automated drift detection algorithms are being developed to identify subtle shifts more quickly than human reviewers can. AI-assisted monitoring tools promise to reduce operational burdens, flagging anomalies, and even suggesting corrective actions. As AI systems become multimodal, handling text, images, audio, and video monitoring will expand to cover performance across these diverse channels, capturing risks that emerge when modalities interact. Integration with lifecycle governance is another anticipated advance, linking monitoring data directly into governance dashboards, audits, and decision-making structures. These developments point toward a future where monitoring is not an afterthought, but a deeply embedded feature of AI operations. Practical takeaways emphasize that monitoring is a frontline safeguard rather than a back-end formality. It detects drift and failures in real time, allowing organizations to intervene before harm spreads. Bias and fairness require continuous attention, not one-time audits, with alerts and reviews built into operational routines. Tools and infrastructure provide scalability, ensuring monitoring can keep pace with large deployments. Embedding monitoring within governance structures ensures accountability, aligning day-to-day oversight with organizational and regulatory expectations. For practitioners, the takeaway is that monitoring should be designed as an active, adaptive process, one that evolves continuously to protect both system integrity and user trust. The forward outlook suggests that monitoring will become more formalized and required across industries. Stronger regulatory requirements for continuous oversight are expected, driving organizations to adopt standardized practices. Automated solutions will see wider adoption, reducing human burden while improving consistency and responsiveness. Enterprise observability platforms will grow, connecting AI monitoring with broader system health dashboards used in information technology and security operations. Integration with organizational governance frameworks will become the norm, ensuring that monitoring data feeds directly into risk registers, compliance reports, and board-level reviews. This outlook reflects a maturing understanding that monitoring is essential not just for system performance, but for organizational credibility. A summary of key points consolidates the episode's central themes. Monitoring provides continuous oversight of deployed AI, ensuring early detection of failures and alignment with intended goals. Drift takes multiple forms: data, label, concept, and feedback, each of which can degrade performance and reliability. Metrics, infrastructure, and documentation transform monitoring into a systematic practice, while ethical responsibilities demand transparency and fairness. Organizational roles, collaboration, and continuous improvement ensure that monitoring evolves with risks and expectations. Collectively, these points highlight that monitoring and drift detection are central to building resilient, responsible AI systems that adapt to change. In conclusion, monitoring and drift management serve as the operational heartbeat of responsible AI governance. By tracking performance, fairness, and reliability over time, organizations protect users, uphold compliance, and preserve trust. Ethical responsibilities add urgency, ensuring harm is detected and addressed early rather than hidden or ignored. Future advances will bring greater automation, multimodal coverage, and integration with governance systems, making monitoring both more powerful and more efficient. Organizations that invest in robust monitoring today position themselves to meet tomorrow's regulatory requirements and societal expectations. Looking ahead, the next step in responsible AI governance turns toward incident management, examining how organizations can respond effectively when monitoring reveals that systems have failed. Thanks for tuning in to Bare Metal Cyber, your trusted source for cybersecurity educational materials, news, and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.